All right, I'm going to start sharing screen. All right. I hope everyone can hear me. Thanks everyone for taking the time, and we did one of these last year, and it's good to do one once in a while since the project evolves. And thanks so much, Joanne, for following up and then driving this through and getting this like pulled together. This is like really awesome, and I think the entire community would be like very grateful to you. um cool. We have a pretty informal agenda, obviously, for here. I did put together some slides for just like directional guidance here, and I do have like a Jamboard set up here as well. If we have to like whiteboard and explain certain things as we go, so I'm all pretty set up. Let's go. So high level, this is what I thought about. Feel free to ask questions in between, or we can take it. We can use the QA function here, and if we can, if you want to actually step through some code um, in a in specific asks, anything like we can accommodate that. We'll just start with just like introducing Hudi, what we have in the project today, and just have different areas. We'll pick like the top five most, I guess, used kind of interacted with packages, and then walk through some of the core classes there, how it's structured. But I'll also talk at the end about like I put together like some sequence of technical execution roadmap. So just to explain what are being planned and what sequence and dependency in which they're getting executed, just so everyone has like an idea about like what's coming in the pipeline. Important RFCs, open PRs, I can generally discuss. Um, Sound good? Cool. All right. So I think just lifted this from my Apache Con talk. So recently we put up a blog explaining what Hudi is. Well, Hudi was something when we started the project, right? But it's grown in the open source thanks to all the community and the community contributions. So we took some time to write up sort of what we have in the project, and so here is how it stacks up today. It starting from the lowest layer. I mean, obviously, we are all familiar with these things: lake storage, open file formats. So what we have a set of functionality which amounts to pretty much what a database kernel would have, which is it has some layout, file layout and partitioning, store schemas and file listing. So something that amounts to what is now, I think, more referred to as like a table format, if you will. But we also have like a bunch of indexes that we build on top. We do build a lot of concurrency management control on top of it, as you may know. And we built a full set of table services which can actually maintain the table and kind of like optimize it for either storage or read or write performance or bookkeeping, any of these things. And on top of that, you'll have like your readers and writers. This is where there are many engines. We have engines like Spark and Flink, which can like have writers. We also have these platform services which read and write data. So there is a lot going on here. And then, but broadly, we offer updates, deletes, and keys, and all of these things. And the stuff in the stars are stuff that we want to be building towards, right? And then the dotted boxes also represent things that we are actively thinking about. And yeah, on top of that, query engines to Spark, Presto, Trino, Hive, Athena, Redshift, Impala, and then I think there's a RFC out for BigQuery, and then there is also some interest around Snowflake, which we're thinking about. And I've been having some conversations with different real-time data marts as well to see whether there's an external story integration here. So for the goal for us to keep it, easier and easier to manage and transactionally write two transactions and mutations and build pipelines for data on the lake, while we try to interop with pretty much every engine out there, right? And then the platform services, of course, we have the streaming ingress transformers. Streaming ingress is basically the Delta Streamer tool, and you get commit notifications for into Kafka topics or HTTP endpoints. So it's like a whole bunch of upper level functionality that's built out. The latest being the Kafka Connect kind of implementation that we've landed an initial version for, and we're trying to get this out in a more workable shape before the point deployment ready for like point 10. So that hopefully presents like a good picture for the project. And if are there any questions about any of these components, or I can go to the next part, which is I'll start explaining how the different folders in the project, what do they do. All right, I will proceed. So this is literally the how it shows up on GitHub. So I can explain each of these as I go. What code is where. So Docker basically contains this Docker demo that we built a while back, which brings up essentially Hive, Spark, Presto, even like a Kafka cluster, and all of these things, so that you can actually start making changes. These demos do need some sample data, so we do have them too. And I think this should probably move out somewhere, but the stress test, which I'll talk about later, it has a bunch of YAMLs that we used to test Hudi. So those are all out sitting here right now because and CLIs, you may have used CLIs for administration, repair tools, monitoring, looking at commits, all of those things. The CLI lives there. The Hudi client actually is like all these writer code which represents the different table types or different actions that are in Hudi are all here. Any code around how we execute, let's say, cleaning for all these different writers, they're all here. And Hudi Common has the basic transaction coordination, pretty much the Hudi file group, and then how we do commit events, and then how we reconcile them. Everything from there to all the basic classes that are used across different modules to read and write files. All of those are in Hudi Common. And examples, we have like some minimal set of examples here. They need a lot more love. But I think, yeah, it's basically some code examples for you to get started. And so Hudi Flink actually depends, for example, sits on top of the Flink writer inside Hudi client, and it integrates essentially Flink's APIs on top of our writer. It's basically where that Flink integration happens. Hudi Hadoop MR, similar thing for Hive, and has all the Hive reading specifically, right? As you know, we allow writing from Spark and Flink, which offer more, which is where most people write a lot of the data pipelines in, barring maybe Hive. But we then allow reading from all these different engines, right? So here, right now, what we have is a Hive integration with all the different input formats that you need to make the Hudi data queryable through Hive. And obviously, in some cases, these input formats are directly used for example, in case of Impala, or even the older kind of ways that we used to do Spark. These get used, or Presto's MOR snapshot queries. These also get used in different engines as the baseline implementation for Hudi merging. I think I got disconnected. Can you guys hear me?
Yes, you can.
Okay, cool. All right. Yeah, just to recap, the intake test framework, this basically has a bunch of DAGs in which you can write like a do some insert count verification or something to validate it work. So you can author test.
So Vinoth, I think we are losing you in between.
CR space.
Sorry, Vinoth, it's a bit on and off. We're losing you in between.
Yeah.
Okay. Is it better now or?
Yeah, it's better now, but sometimes in between, like for 10 seconds, we lose you.
Okay. Let me try to grab my. Hey, I'm back. Can you guys hear me well now? I grabbed my neighbor's Wi-Fi.
Yep.
Yeah.
Yeah, sorry, I don't know what's with my Wi-Fi. It's been acting up. Okay, assuming you can see my screen and you can hear me, I'll proceed.
Yeah, we can see and yeah.
Okay, so all right, so I think I was explaining the intake test framework, right? Where you can actually write DAGs let's say, for example, you want to test Hudi a lot more before you roll out things in your own production environments. You can actually write YAMLs here and run it inside your Jenkins kind of environment, as long as you can run a Spark job of sort, and then it can actually run you can author some complex scenarios here, and then be able to test some of this. So Uber runs some versions of this internally, but we would love for more people to like author some YAMLs that are specific to you, and then hopefully we can get better testing and then easier way to certify releases this way. So that'll be something worth checking out for folks here who are looking to get like much better at like doing deployments and picking up new things. And anytime there's any issues with my audio, I think just ping me on the questions or something. I don't know. Yeah, the new Kafka Connect sync. So like as you all know, Kafka Connect is a popular way to stream data from Kafka into various sources, including HDFS and trees. And we are trying to build like a Kafka Connect sync, which can actually transactionally commit data into Hudi tables. And then right now we have support for append-only data on MOR. We are trying to work through a few issues to get like all the table services wired in and everything, but all that code sits here. Spark data source and SQL implementation, which is what a lot of people use to write Spark jobs. Either we added Spark SQL support last release, so that sits here, and then any Spark streaming sources or batch sources that you write, all that code sits here. Hudi sync is how we sync Hudi data out to metastores. We do support multiple metastores. For example, you can have the glue catalog and a Hive metastore, or there are also a lot of requests to sync this data out to the data hub / Amundsen / like all these like other meta stores as well. So you can actually write more to sync this out, and this is the mechanism that is getting extended to help us write keep BigQuery or Snowflake table definitions updated, as well as we can land data into Hudi. So and then like we have our own, I should say, meta server, which we have been having for a while. This currently serves all the file listings from the driver to the executors, so that we don't list the file storage from executors directly. And there's been like a long pending thing so every time we start this, where we want to make this into like a server, and then like, people so the community kind of like whenever we sometimes get like mixed responses to whether we want this or we want like a zero deployment serverless architecture for Hudi, and so it getting deprioritized. But I think we're gonna probably do more work around this. And again, this is wrong. This is more where all Delta Streamer, all the sources, everything live, and packaging contains all the different bundles. And recently we moved all the design documents, RFCs into this folder here. The old ones remain in CVKey, but we'll slowly age them out here so that the code and the designs can evolve together. And bunch of scripts and IDXL files. For today, what I thought was we can cover these in this order. We can start with Hudi and just explain the lower file layout, transaction coordination, all of those things. Move up into the next level, which is all the writer code, and then look at Hive integration, where we can see like some reader code, and then we can look into the Spark implementations in the Delta Streamer and look at how it reads and writes data. That's what I had in mind, but let me know if you guys want to take it in a different direction or anything else. I take it as an yes. And okay, so we can start with Hudi common. And so everybody here, are you like familiar with like the basic concepts in Hudi, right? Or do we need to also like talk about it a little bit, like copy and write, MOR, timeline, commit, delta commit, like all these terminologies? Are we familiar with those, or should I spend some time just quickly laying out how the data looks on disk, and would that be helpful?
That would be helpful, Vinod.
Okay, cool. All right. All right, so I have this thing here called the Google Jamboard. Let me try to sketch this out. So, and pardon me if my handwriting looks, horrible. So, at a very high level, right? As you all know, what you do in Hudi is you can write transactionally, and by write we can do upserts, deletes, inserts, and then a lot more, right? And then you get a Hudi table, if you will, and then the readers or the queries can actually read a transactional snapshot, or it can also consume change feeds out of the and incremental queries out of the table, right? So this is at a nutshell how we do it. But so if you translate this to some logical design, so let's take like start with good old Parquet tables on HDFS or S3 or cloud storage, how it looks, right? So you usually have like the table. It has a bunch of partitions, right? These are all partitions, and you usually have files, right? So if you look at what problem we want to solve, we want to be able to like update and delete and insert, right? Insert is adding new files. Update and delete could be like doing certain things to reflect those. So the way we do it is we have two modes. One is even before that, at a higher level, we we need to essentially write data and then commit somewhere. So Hudi has like a dot Hudi folder under every table. So you can think of this as like data, and then this is all the metadata, including the transactions. Everything lives under .hudi. So directly under .hudi, you will find things which are like timestamp dot some action dot some state. So for example, t1 dot delta commit dot requested in flight, and then this will go away the extension, which means it's complete. So so immediately under the Hudi timeline is what we call a set of files. You'll find a set of files like this, and this is called the active timeline, meaning so these are all the transactions which are being currently written or being how do I say it? So this is the amount of metadata that you need to retain to serve all queries on all writes, including like incremental, read optimized, all of this. So all of that state goes into active timeline, and then as more and more things happen, right, we move this over to a dot archive folder, which I think is today just for like purposes of just like auditing or anything from the CLI. But but we want to actually use this down the line, but I'll not get into those things now. But the idea of this design is, unlike formats where you have the metadata just growing with the amount of data that you have, right? This keeps a constant amount of metadata in the table, even as your table grows for like years, right? So, but at a very high level, what we do is we write some files or do, into the data, and then we write like an entry here. Think of this as a state machine. Everything starts from a requested state. It moves to an in-flight when the kind of the action is getting it happens. Then it moves to like a completed state, correct? And or it can remain in in-flight and then it gets like rollback. So this is basically a state machine in some sense, where we denote, we use this timestamp to order every action and to sort of like do MVCC based resolutions and all of that. And this lets other parts of Hudi know that what kind of action you're doing. So this is very important and a distinction where, for example, like actually differentiating between, like, let's say a clustering, which is like a replace commit, um, and or even even if you take like compaction and delta commit, right? A more simpler example, they know that the delta commit, for example, the delta commit handling code would know, hey, there's a compaction that is being done on this file that I'm trying to update to, and then it can do like concurrency control around that, right? So we've written a lot of this kind of code where these actions are aware of each other. They're not treating the table as like a dumb set of files that you like, publish no snapshots to, but they are actually more intelligent in actually resolving these conflicts and letting more writing and reading happen in parallel, and more concurrency, the better, right? So pulling back, that then coming back to this is roughly the metadata, right? But coming back to the data itself, if you have an update, then you have two choices, right? One, we can, let's say this update affects a file, like the file here. We can either version this file and then call this f, and this is f prime. This means you take a lot of hit on the right side, and while on the query side you can, instead of previously a query would have read these files, instead now it reads this file, right, to get value for the partition p0. So it has like pretty much zero read amplification. So essentially the amount of bytes you read for to answer a query, so it is no read cost basically, extra cost being added, while on the update side you take all the hit of like doing this, right? So this is what we call as copy on write, because just like sort of block based storage, the minute you have like an update, you just like copy that thing over, right? The other form that we have for update is, for example, we don't want to do this, right? Like, for example, let's say you have a lot of deletes to a bunch of folder partitions. If you did copy and write for all of them, what you would see is you are pretty much overwriting the entire table, right? So people have to then do tricks around it where you have to only do the delete every so often, and then if the delete fails now, then you are kind of like um, screwed again, or you have to like do a lot more coordination to manage it, right? So what MOR does is, the MOR tables, they actually append a delta log. So the very time you append or update or delete the table, we pretty much figure out which file you're going to get actually update to, and then write a delta log entry close to that file. And then the queries can have an option now. You can either say, hey, well, I'm doing this for GDPR kind of like enforcement, so I can keep deleting, and then it's okay to just keep reading the base files, right? And this is called what we call a read optimized query. So you need not actually pay any cost of merging if you don't want to. But if you do want the latest snapshot, where you are actually having a more real-time in just kind of like scenario, then a snapshot query can actually merge these two together and then hand you the records. And obviously an incremental query can read the log and then serve a stream of changes without you having to store like a side table or anything really. And then the incremental changes and everything is like a single data layout, so it's all kept in sync with each other transactionally. So that's the high level difference between like a copy and write and an MOR table. Any questions? Okay, sounds good. So with that sort of like background, let's actually go back and then we can refine this as we go. So I have the IDE pulled up as well, and we can actually start walking through these packages a little bit more. And if you look at Hudi common, and I'll first explain for everything. I'll explain the package generally, and then we'll talk about the specific classes which are more important, right? So the Hudi common, as you can imagine, like has a whole bunch of. You guys can see my IDE, right?
Yes.
Okay. All right. Thanks. So yeah, so there is a bunch of like helpers and everything here, but you will bind. So you'll find a lot of the there's the Bloom filter implementation that we have. We implemented a version of dynamic Bloom filters, except we also bounded them. So you'll find that we actually implemented a fair bit of like data structures, storage structures in this project. They all usually sit here. And this is some bootstrap related code where you can bootstrap existing data without having to rewrite them. And this is like all the base classes that we need for configurations. The most important thing here is we did this last release where we added this class where every single config property in the class in the project has is written like this. So it's like kind of pretty nice to read. And then the other thing is we configuration up to date automatically by just like using Java reflection, writing some script to generate the MD files. So this is where I think if you go and look at the class hierarchy, you would pretty much find every configuration that is due in this project. Oh, that okay. I think that so sorry. Like that's the Hudi config class. So every prop config is like this, but then every we have different classes for different parts of the configs, and it's all here, right? And the most often question I get is why does Hudi have these many configs? And the answer there is we always thought about Hudi as more like a database kind of engine. So a lot of them have configs, and when you write stuff to run at like a larger deployment, you tend to introduce a lot more configs than probably what you need to do. So we are trying to make these defaults much more user friendly out of the box rather than having fitting them to scale a lot more. But in a nutshell, every database that's on the planet, you will find that they have a ton of configs and they are meant to be written that way, right? But anyhow, that side note aside, you'll find most of the configs here from this class. So the engine, so good. This is a good thing to understand. So a good chunk of Hudi code is like let's say for example cleaning, right? Essentially, you need to get a list of files to delete and then do a map and then delete it in parallel using Spark, right? So all of these kind of code was duplicated across engines. So what we did was we introduced this Hudi engine context, which can now be either Spark, Flink, or Java, or the query engines use something called a local engine context. But high level, this exists so that we can write a lot of these table management like services and all of these things without duplicating the code. So we can pass a function, and underneath we can do it using Spark or Java or anything else. So that's what it is, and we are also introducing new abstractions now to abstract whether it's an RDD or a list of records as well, to further reduce the amount of code duplication, and then reuse more of it this way. File system has a bunch of things on a consistency guard. I think a lot of this you need not worry about now, given if you're an AWS user, and of course if you're on Google Cloud, you already didn't have to worry about it. So yeah, a bunch of this thing exists for, I don't know, some other blob stores which have this kind of eventual consistency thing. So this package generally has anything that we've optimized around a file system itself. So for example, we do size aware. So when you write through, we have this Hudi wrapper file system, which wraps any underlying file system that you use. The reason is we can then get metrics out of it, and also we are able to do things like consistency guards, and these things are pushed at this layer, and we can also measure size. So if you want 1 GB files, we can actually measure the writes as they're happening, and then we can close a file and give those signals to the upper layer writers as this is happening, so that we can keep the file sizing and whatnot. Any questions so far? Is useful, like the way we are going, or if please feel free to suggest any way. Sweet. Okay, so these are all just functions that you can pass to the engine context, so not matching. And this is the main implementation for concurrency control for log provider. We have log providers for Hive and Zookeeper, and I think we are going to land one for DynamoDB. So yeah, that's metrics. Okay, so this one's good to understand. This, I think, honestly should be broken down a lot more. It's gotten pretty big now. This actually contains all your payloads, for example, right? And payloads in the project, as you may know, so this is the entire hierarchy of the payloads, and payloads are pretty much the other sort of more like a unique design choice inside Hudi, right? Where payloads not only are useful when you're writing to the table, but they also describe how you will later merge the records when you're doing a merge and read query or doing compaction. So it takes effect. So it high level has the 3 methods, which is when you have a bunch of inserts, so a bunch of change logs coming in, how do you combine them to get one value before you can do index lookup and everything? And the other thing is, how do you extract value for it when you're inserting? How do you kind of merge and update that? And we've written many payloads in the project. One has behavior of overwriting with the latest, and there is rewriting empty. When you use empty, we delete stuff, and there is a payload that we wrote for the metadata table and so forth. So you'll find all these payload implementations here, along with basic classes like Hudi record, Hudi key. Hudi record is basically, as you know, it holds a key and some data, and then some information for kind of the index to annotate and then get updated after you write transactions. So these are all things actually you need to write this kind of like an experience, right? Where it feels like a database where you keep some change logs, and then you say upsert, and it can do all these different things and maintain unique key constraints and all of that. So all these classes exist here. There is like there is also these other classes where the two other ones I would call out are the Hudi file group, which is the base model for us to reason with anything, right? So each one has like a ID, and then it has a map of file slices. So I'll kind of like briefly explain what these things are here. So in Hudi terminology, like before when I was explaining copy and write, merge and read, I was speaking more like kind of like informally, right? So what we do is let's say copy and write, for example. So there was a f1.parquet before, and then remember when I said that you can version this into f1, let's say prime.parquet, right? So but all of these share the same ID f1, right? This means so we deterministically map an incoming record key into a single like ID, right? This is pretty much the mapping that the index helps you figure out. The reason why we do this kind of like mapping is so that we can actually keep the delta records, like when we do the deltas kind of like close to the base file, each base file. That way each base file has to only scan a limited amount of data, right? If a base file doesn't get updated, it doesn't have to scan all of the data, right? So there are like really good advantages to doing this in terms of like when you do query performance or even ingest speed, if you will. So pulling back, each record key is mapped to a file, file like an ID, and all files that are written, for that ID is what we call a file group. And then each combination of, if you now get Memor into the mix, each combination of, let's say, a base file and a log file, let's say you produce this at like commit C1, delta commit 2, delta commit 3, delta commit 4, have this log file. Then you decide to compact this this base file against these logs and write like a compaction commit C5. Then you pretty much have two file slices. So you have, this is the file group, and then this has two slices of data. And we use this pretty much, this is our basic way of reasoning. And each of these slices and blocks and everything is stamped with the commit time. So for incremental query or snapshots or anything, this helps us actually find out easily, okay, this is the cut of the table, snapshot of the table at this point in time, right? So that's why we have an ordered. So this ordered data structure here, like a tree map, where we have the commit time and it maps to a bunch of like file slices here. And these file slices have, yeah.
Sorry to interrupt. Can you come again on the file slice and file group concept for the delta immutable concept?
Yeah. So, by the way, this is 2 hours, right?
2 hours, yeah.
Okay, cool, yeah. All right. So yeah, what I was saying was, let's take how okay, let me start over. So typically, what do you do in a delta like MOR table? You do delta commits, you do some writes, and then when you do these four delta commits, let's say, let's say you do these 4 delta commits. What's going to happen is, let's assume for simplicity, the file only has like the table only has like one file group. What's going to happen is it's going to first write a Parquet file, because that's at least how it is today. So you will produce a Parquet file, let's say f1.parquet, right? And then it'll also have it'll actually be called something like f1_1.parquet or something, right? So it gets, what I'm trying to say is we generate first time you write, you insert data, you're writing new data, then you assign a new ID, this F1, which is typically a UUID in code. And this is what is called file group ID. And then what happens is anytime you, let's say, delta commit 2, 3, 4 are updating some records within this file, we write like delta blocks for this, right? And then so each of the blocks is stamped with this is stamped with 1 internally, this is like 2, 3, and 4. And then now you decide that, hey, I want to compact this thing now. Then the compactor turns this into like a new Parquet file, and then at like let's say you are running inline compaction for simplicity. It turns it into f1 underscore phi dot Parquet, right? And then you continue to write like say a couple of these other delta commits, right? So what I'm trying to say is these two are what we call as slices, where a slice is essentially a base file with all the logs that are delta logs that are queued up on top of it.
Okay.
Right. And then a set of all these file slices belong to the same file group ID F1. So in some sense, if you can think of this entire thing as another log, as a self-contained log, right? Because we encode any changes that are happening to all records here within these log blocks. Even if you write something and roll back, or if you delete, you can add a delete block, a data block, and all of these other things, which lets us be like kind of like we can then the compactor can take this and apply it and then produce newer things. So logically speaking, this whole thing is called a file group. This thing is called file group F1, and then which has two slices, one at commit time 1, and this map is going to have like two keys where it's going to have the base file mapped to this.
Okay, thanks.
Right. Cool. So yeah, that's pretty much what you have is the base instance file. What is the base file? An ordered set of log files. So these two are pretty much what we pass everywhere to read files, filter, do anything really. So yeah, these are the main POJOs that you need to understand in the project. So moving on, we also have a bunch of like all the log blocks that we talked about. As you can see, we encode the deletes here, all of these things, and all of these things are stored here, have blocks. There is a lot of this code to read a file slice, write a file slice. We are actually working on improving all these lot more. Anything to read the log files, write log files, all of those things are here. And then we also have what we call, anywhere we are in the project, you're looking for code to merge these log blocks together. We have, you go to this abstract Hudi log scanner. And then we have two kinds of log scanners, one which actually merges it, the other, a lot of people have just like inserts, right? I mean, just append only data, but they want to like write quickly and then compact later. So you can also do like an unmerged record scanner. There's also a merged record scanner and so forth. And the main other thing here is these two things actually. So there are three main classes here that I think that's pretty much all the other important ones. So talking about so anytime you upgrade or downgrade or any like all these version migration classes are written from this, and So remember I talked about the metadata, the .hudi folder, the active timeline. So essentially there are classes here which can read list.hudi and then read all these like different action files that we write here. And then they expose a lot of functions to either commit new events to the timeline or like remove them in some cases or read them out, read the metadata inside these things. So all of that is in Hudi active timeline. Hudi archive timeline is pretty much like, all the things that it has logic to that can expire older actions from the active timeline into that. And Hudi instant is the base sort of thing where what it really has is a state, like I mentioned, right? The state can be, requested in-flight completed or like invalid, and it is something internally used. And then it has a name of an action and then the time at which the action happened. We are also looking to add the actual transition time. This is actually the time at which the action started, right? But for us to get some like other total lock-free concurrency between writers, we probably need to also denote when a particular action transitions into a particular state. So we are also going to be like working on that, and this is probably the first time this has changed in like 3 years or something like that. Yeah, so most of the code around like timeline, which is the .hudi folder, reading, writing, doing anything is in this folder. And yeah, so this is the meat of all the transactional code in the project. This and the table meta client class. So maybe I'll start with the table meta client because it paints a picture. See, everywhere in the code, you need access to, you're trying to write files, then you need to know, like to do that more transactionally, right? So you need to understand the transactional state of this thing. So Hudi table meta client is pretty much that. So if you look at it, it essentially has what we call a table config. So the thing yeah, maybe we should like spend a little bit more time on .hudi here. So .hudi has some important contents, right? Something called hudi.properties. So this is all the table level configs. So for example, if you're using Spark SQL, what is your primary key? What is your partitioning field? All of those things are stored in .hudi.properties. And then you have the active timeline here, right? The thing that I talked about where you do ts.action.state sort of thing. And then what you have is the .archive folder. Then what you have is a .temp folder, which we use to clean up like temporary, like we use as temporary storage for when transactions are running. We have markers and everything to make sure we can automatically clean up. Let's say you have a write, for whatever reason, you run a large batch job and then you go to sleep and then it was failing through the night for whatever reason, right? So what this can now cause is a lot of like, like incomplete or like new, like a lot of data written into storage, but it's not cleaned up, correct? So what Hudi will automatically does is instead of like, letting it fester, so it will actually roll back any in-flight or like very inactive kind of transactions. And we write some metadata called marker files here to make sure that we can actually go and clean them up more efficiently. We have like a blog recently out around that, and we reworked this significantly in the last 0.9 release. So that store is held here, and there is also like a .metadata, which is going to hold like another internal Hudi table which will hold file listings, and then we have like PRs out to hold record level indexes, range indexes, and like all Bloom indexes. We are essentially going to move all kind of indexing into the metadata here. So yeah, this is what it has, and what the Hudi table client really does is expose, like, manage these folders and expose ways for you to access the timeline, the archive timeline, get the table config, and sort of like anything you really need to, like a file system interface, like instance to operate on the database, all of those things, right? But the real meat of this is the the file system, the abstract file system view. So imagine, so remember how we were talking here about file slices and groups and all of that. See, so when you want to do a query, you need to do some logic where you want to say, hey, this is the latest committed, this is all fine, but somebody needs to kind of like read the timeline, read the list of files that we have, and then provide snapshots, right? And then say, okay, give me the latest set of data files, sorry, like the base files. Give me the latest log files for this file group. Give me all the file groups that have changed, or all or file slices that have been written after a point in time. So we need all these different queries and different views, if you will, of this kind of like file system that we have underneath. So this is the job of the abstract table file system view. And it has actually all the transaction reconciliation, all this code is here. So if you look at what it has, right, the kind of APIs that it supports, it obviously has some things to build the view itself. But once you have it, you get all these methods where you say, actually, hang on, like I think it'll be easier to look at the interface. So the stable file system view, as I mentioned, you need these methods basically. You need to get all, like for copy and write, you're just dealing with, or MO or snapshot query, you're just dealing with base files. You need to get all the latest base files for this partition on a given file group ID. Give me everything. Give me this before a time, after a time, in a range. And then you also need this supported with the file slices as well. So yeah, so these kinds of things is what this implements. The base class has a lot of this actual base implementations for this. And as you see, as I mentioned before, we have many ways of storing this file system metadata in the project now, right? Which is in the timeline server, we back it by RocksDB, so that it's like super fast. And this is actually how all your Spark jobs are actually running. They're all, for example, they're all running like this, where you have the driver stores a local RocksDB instance, and then all the executors that you have, whenever they want to call for, hey, give me the latest base file or something, they actually make a remote call here, and then the driver actually goes and tries to fetch it out of like DFS, and caches it into here, RocksDB, and there's also a memory one, and then sends it back. So each partition is just listed exactly once, and then you can actually scale out pretty well. But obviously, with the new metadata in table as well, the metadata table is also like one of the backing implementations here. So as you write data, the metadata table gets like populated. You can also fetch listings directly out of this, and without having to read from storage. So I mean, it is not enough to just have the metadata table and access it directly from here, because you'll be still opening so many files, right? And if you're an S3, for example, the number of calls you reduce to S3, the better for you throttling and everything wise. So what we do is we open the metadata table once here, read it and cache parts of it as access comes in, and then we serve it out over the driver to the executors. So in effect, we've built like very kind of like localized scaling for the metadata. Your metadata for your job scales within your job, basically, right? And that's how this works. And sorry, like most of this code is here, which is this is the metadata backed file system view. So there's a hierarchy here on how different implementations get this out, but this stable file system view is the basic thing that you need to understand. And all of the core transactional logic is here. Like for example, how remember earlier I was saying how the compactor compaction and delta commit work with each other to like bring you async compaction. All of that transaction logic happens here, where this will hand out a file slice in considering what has really happened on the timeline. And it pretty much like you can think of this as the transaction controller kind of like code, which is not bad that this is 1,000 lines, just 1,000 lines. Any questions so far?
Hi Vinoth, just had a question. So this view provides, given a file ID, we'll get to know like different versions of the file and all. For suppose if we have a primary record key, if you want to know like which file ID it belongs to, or those kind of queries cannot be done using this API.
Yeah, this is just a metadata API. I think you can quickly look at Hudi read client in your IDE. I think I saw this question on the Slack, I think yesterday. Yeah, we don't expose the point lookups yet through SQL, but for like some one-off use case, there's an RDD level API that does this actually, but this won't give you that.
Okay, yeah, got it.
Cool. All right. Yeah, there's a bunch of synchronization around all the transaction management code. So, and yeah, moving on, you all probably have interacted with key generators. This is basically the key generator interface, and we have one for Spark, and where we don't want to do the row conversion, like to Avro conversion, right, for the row writers. So we use this to actually implement a row-based one. But at a high level, it takes like the base one takes like a generic record and gets a key out of it. That's pretty much what it does. And yeah, that is pretty much the Hudi common module actually. Anything before any thoughts? Anything before you go to the next one?
So one question, Vinoth, a naive question. So we currently use the RocksDB as well to load. So for example, we want the latest best files, right? So we'll read it from the RocksDB, or it will actually open the file metadata and just give us the information when I am using a Spark, right? A Spark data.
Yeah, if you turn on metadata, it will use metadata table to read it out of. If you don't use metadata, the default is it will use. I think default is memory actually. I think it will cache the listing in memory and serve it out. That's what it does, I think, by default. But you can make it do RocksDB. But by default, this kind of access where it's getting from the driver, that is what it's been doing by default since 0.6.
Okay. So which usually is the fastest? The metadata table will be the fastest, is it? Or like if I have to find this?
Yeah, there's like different trade-offs here, right? I actually think RocksDB will be faster, right? Memory will be faster than everything, but you need to spend memory, right? RocksDB, you need to spend storage, but it's local storage, it'll be faster. Metadata table, yeah, I mean, absolutely speaking, it's a remote call every time, so it will not be as fast, right? By the way, whatever, even if you put it in metadata table or RocksDB, it's always cached. Like let's say so see, the metadata table will have 2000 partitions, let's say, right? But you're only writing the last one. So we lazily cache only the last one based on what the executors are really asking. So if you think about it, for writing at least, you only cache portions of the file, like the metadata based on what you're really accessing this. This is very kind of similar. I was reading through this other thing called Firebolt, warehouse, or these things, right? These techniques are very similar to what cloud warehouses generally employ, but sometimes it's hard to kind of deliver it in this data lake kind of ecosystem because we're not used to running servers and right, we're used to running mostly jobs. So yeah, it's a little different, but it gives you very high performance that way.
Sure.
And so while we're at it, the other thing that I want to like mention here is, let's say you're running Delta Streamer. This is something that if anyone's interested here, I would love to work with someone to certify it for production. So when you run Delta Streamer in continuous mode or Spark streaming, you can actually we have ability to keep the RocksDB actually updated after every commit. So that way you never go to, like, unless the driver redeploys, you never go to file system at all, right? If we can pull this off, then we can keep most of the table stats we can So the plan is to enhance the timeline server with every, the range statistics and everything else, so that we can do like very fast planning. And then even if you're like, for example, if we do the incremental kind of fetches, right? So if going back to the file system view, that is what this thing is implementing. This incremental timeline sync file system view is basically implementing. So you have the file system metadata till point commit C1. How do you, and then let's say C2, C3, C4 have happened. It has code to update the file system view, whether it's in RocksDB or in memory or anywhere, of new changes as well. That way it's super efficient. The writer can keep writing, you can update the metadata, keep writing, update the metadata without ever going back, right? So, but we haven't turned this thing on really by default. I need some help, like maybe if you're anyone's interested, we can work together on productionizing it. Cool. All right, moving on. I think we spend a lot of time covering Hudi command, which is good in a way because most of the core, the meat of it sits there. But let's also discuss speed up maybe a little bit now that I see that we are 1.5 minutes in. Okay, the Hudi client, right? I mean, I probably named it a little bit, with a more databasey kind of background, which is kind of like what my background is. So you can think of this as a traditional kind of like database client kind of thing. So it's broken up. So every writer code is here. It's broken up into client common. So we've written a whole bunch of code using the engine context abstractions and everything, where we don't have to redo stuff. And then we've extended the writer code for Flink, Java, Spark, so on. So this uses the Hudi common and then builds, writing for all different operations. It builds up a bunch of indexing schemes. It provides a Hudi table implementation, which can be Hudi copy and write table or merge and read table. And these are some basic classes I would like to cover there. But at a high level, starting from this, most of your interactions from Spark. I think if you're using Spark data source or anything, this is hidden from here, but this is the entry point for the lower level client. I think, oh, sorry. Okay, okay, cool. I think it's called the up. So there's like a, so this is the hierarchy here. Pretty much, if you see this, this paints a picture. So there is like a Hudi abstract, Hudi right client, which is extended by a Spark, a Java, a Flink one, pretty much. And then if you look at what this has, this typically has a bunch of methods. I mean, there's some internal ones, but like the bunch of methods mapping to each write operation, right? This is what it has, and then we implement them in certain ways across the different engine-specific write lines, and that's more or less like what it is. And all of these operations, right? If you it usually just delegates to a table object. So the write client is more for like orchestration of things. So for example, you might have noticed, right, when Hudi finishes a write, it also tries to do cleaning, it tries to do archival, it tries to do a whole bunch of like background cleanup sort of activities. So all of those things are implemented here. You can look at pre-commit, and you can see that it is trying to update something. Am I on master? Yeah, driver. Okay. This should change now. Yes. Okay, doesn't. Okay. Anywho. So there is a bunch of like pre-commit actions, and then there's like if you want to understand where, for example, cleaner or any of these other things are getting scheduled from, it's typically the post commit. And for example, like archival is kicked off from here, and then here it's saying, okay, if you want to clean, go clean it. All of this, right? So this basically does the higher level right and gives that experience that you do. But the main API that it all delegates to is this. And if you look at the Spark right client and look at maybe some of these things. So the commit everywhere is how we actually commit to the timeline. And you can see that this leaves the timelines APIs ultimately, make a commit API, blah, 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 and then run these services, for example, and then run table services is where we decide to run, whether there's inline compaction, clustering, all of these things get triggered from here. So that's mostly what's in Hudi Write client. It's pretty like thin otherwise, I would say. It exposes all these like different compact insert, all of these like APIs above. And Hudi table is really, again, like it's one level down. As you can see, it is first broken up by engine, and then you have one per copy and write merge and read. We almost always like merge and read is a subclass of copy and write, and you can see the methods here. Like they're pretty like, again, they're somewhat delegator methods from the write client, except it also has like timeline, and all of these things are hidden into this. So we don't leak any transaction checking logic or anything into write client. We try to keep it simply like as a kind of like an adapter class between the Spark or any other upper level engine specific writers into this, right? And from here on, this is all fully transactional. We don't try to leak any engine specific things into any of these classes, meaning like and yeah, so on each of these, if you notice, they all will again for each action for each table. So for there'll be an action executor class, and there will be one for each engine, each operation, each action that you want to perform, right? So if you're doing upsert, insert, bulk, or anything, I mean, if it's a copy and write table, it's just a commit, right? So all of those will be handled within that. So there are no operation specific classes, I think, for the most part. But this is the main hierarchy. This is, I think we're trying to see if we can make this easier to grok and then make like a little bit more nicer than having a pretty deep hierarchy like this. It's pretty deep, as you can see. So you start with the base action executor, which is pretty simple actually. All it does is takes a bunch of these configs and table instances and everything. It literally has like a execute, that's all, right? And then you tell what kind of result you're expecting, and it just returns you that. It's pretty dumb that way, but we managed to create a hierarchy, extend this, where there are like base things, like for example the base commit. If you're interested in writing alone, for example, there is a base commit Spark commit action, base for each engine, and then within that you will see that there is like, then here is where we actually take some of what I said back. Here is where we fork out into different, write operations. And then if you look at, so if you want to understand how insert prep is implemented on copy and write for Spark, you look at one class and then trace up. That's it. Yeah, this is where most of this kind of like code is. And let me make sure I'm not missing anything big. Yeah, code these. Okay, Hudi index. So, all right. Maybe it's a good to spend like a minute on what really happens during a Hudi write itself, right? Hudi write path. Understanding this is good because Hudi write doesn't do what your df dot write dot parquet does. I mean, I know that's how people like to think of it, and our usage should be as simple as that. And we are, probably like we should remove key configurations and everything, and we can achieve the user interface. But this, what will it do? It will have a data frame and then write each one into Parquet files with some partitioning, maybe, right? That's all it does, correct? But this is the Parquet dial. But this is not what Hudi does. Hudi gives you way more functionality, and which is, let's say you take, there is like some input data frame RD something. First, what you do is, and I'll talk about like this in partition so that you. So first of all, if you're extracting CDC change logs from a database, you have to dedupe or merge things, right? Like otherwise, let's say you have your we are Uber and then you're storing trips. A trip gets updated many times between the job runs, then you're gonna have many trip runs here, right? So what we first do is we do like kind of like one shuffle phase here to do like kind of what we call pre-combining. And pre-combining is done by default for upsert operations, where we try to merge things in the input into a single record. This obviously is way more efficient than writing multiple duplicates and then merging them later on storage. This way, every query has to merge them on storage, right? So instead, we do this once within batch. And then what we do is, now if we have to figure out whether these are inserts or updates, right? So we take this and we send it into this kind of like indexing component. So index will basically, we'll do a lookup here where we tag quickly, hey, this incoming record is in this file, right? If we know that pretty well, then we can just like go write the file and then get out, right? Instead of just logging a whole bunch of things here and rewriting a lot of data down the line. So this is the indexing step that happens I'm describing an upsert, by the way, like, right. And then what we do is then you need a whole bunch of like, storage optimizations, right? Which is you want to size files, then we try to cache your input. This is where I think a lot of people run into trouble by, even they're doing very large writes, they don't turn off the caching, and then suddenly like there's so much extra memory you need, and the Spark job is filling or something like that. We profile the incoming data, we understand how to pack this data onto disk so that we can achieve file sizing. So we size the files on the fly, and then we again partition it so that you can send batch all the updates together and all the new files together, right? So updates, depending on MOR or COW. MOR, it will go append something. For COW, it will version a Parquet file. But you don't want to send all your updates into different partitions, right? You want to bring all your updates to a given file into the same Spark final partition. So as you can see, it's like kind of like doing like a lot for you, and this pipeline flow is also something that is controlled from the commit action executor level. And then this is the final kind of like write partitioning. So there, I mean, and then once you write, obviously you updated something, you had some inserts, right? You assigned it to some files. Now the index needs to know, right? So you need to go update the index and then commit. Something like a insert would completely skip this. For example, that is why we try to differentiate between an upsert and an insert instead of just saying, df.parquet, just write something, correct? So we can skip this. Bulk insert, again, doesn't basically do any of the storage optimization pieces. Insert will skip this. Insert operations will skip this. Bulk insert will skip both of this, because it's you're saying it's bulk, like batch writes, not incremental writes that are easy to cache. And yeah, none of these are done by bulk insert. So yeah, Hudi also essentially gives you a pipeline that is sort of tailored towards different use cases. If you're just batch loading append only data, I just use bulk insert, right? And then if you're incrementally writing anything, consuming change logs, change streams, use upsert, insert, delete. That's the high level what it does. So yeah, so coming back here, yeah, quickly, write status is the object which returns, after you do like here, after anytime you do a write operation, you return a write status back. That's how it works. And the other parts, maybe conflict resolution. I'll just talk over these conflict resolution strategies, what you need to implement OCC concurrency control. There's a Hudi IO handle. This one's worth looking at. The Hudi IO handle implements. Remember when we talked about this, we said, oh, you append data here, you merge data here, and all these things. So it encapsulates all IO operations done on a single file slice. That's a good way to like look at IO handle. So there are read and write ones to read and write from file slices. For most of these read ones are doing some metadata fetches for like indexing, and the write ones, are doing essentially merge handle, which is whenever you version a new Parquet file. Create handle is writing new base files or Parquet files. Append handle is when you're writing new data into the log file, right? And to quickly cover the indexing, we have many index types, and there's like a nice blog around it. So the Hudi index, which says update their location in the index, and then roll back the index and all those other things, right? And for Spark, we have like, this is purely for testing, but we have like a Bloom filter based one. We have a join based one, which we call index, and then for base, yeah, then I think like one Flink index, which is backed by their in-memory Flink state, which is, I think, is checkpointed out. There's also a join based one there. And so the one thing I forgot to mention, if you're wondering about all code related to metadata, they are in Hudi table metadata. Like, there's different metadata implementations. One is backed by file system, one is backed by Hudi. And between this and the file system view, so this fits one layer below the file system view right now. But over time, this may become more parallel APIs. On the writer side, there is like Hudi metadata table writer. Sorry. Yeah, essentially, anytime something happens to the table, like some action happens, we update the metadata using this. So right now in Hudi, actually Hudi can work with either file system backed metadata or this metadata table. In some sense, if you think about it, right? I mean, if you have a HDF, if you're still on something like HDFS, or like a pretty fast file system with a pretty fast metadata listing layer. HDFS stores all listings in main memory, like in a RAM, right? So it'll always be much faster than reading some file doing storage. So we try to provide all this pluggability and options so that you can tailor it for based on your deployment. Yeah, quickly moving on. Just feel free to stop me at any time. So like we talked about this. So yeah.
Hey Vinoth, yeah, I have a question regarding the logs. So I know that there's a PR open to write the failed records, which to the Hudi error table log. But how do we get meta for how many? Can we get meta for how many records have failed to be written right now? Or is there any way to get some info regarding those?
Yeah, this actually is passed back except to really expose that in the it's not exposed in the Spark SQL, like Spark data source or the upper layers, right? We actually have these things and some like yeah, I think we have to expose a Spark data set client which like works with data set rather than RDDs, and you'd be able to get some of this out for now. If you actually want not the error table, but get some programmatic access to the things that failed, I think please, I think that's what we should do. I think, but there is support for doing it at the RDD layer because if you go to Hudi Spark, I'm assuming Spark. Correct me if I'm wrong. Sorry. Yeah, if you go here, all of these things will return. Let's say you do an upsert, or like, yeah, if you do like anything really that is upsert. Yeah, here you go. If you do this right, you'll get a Java RDD of this. You can set auto commit to off, and then what you can do is you can go inspect this and choose to whether to commit or not commit the transaction, right? And in fact, the Hudi Spark SQL client actually does that. It is there are too many errors, it doesn't commit or it does something like that. So this functionality is in, but I'm saying it's not just exposed out to the Spark layer yet. Please raise a Jira with your requirements if you would like to see this in some shape.
Sure. Thanks, Vinoth.
Okay. Moving on, I think this gives you a good sense of how copy on rewrite snapshot queries work. So if you look at it, all we did was we just extend the Hadoop, like Hadoop MR, or the Hive rather, like Parquet input format. So all we do is some basic filtering using the meta client and the timeline and everything to say, okay, this is the latest commit, and then this is the latest, set of like snapshot for the table that you're asking for. All of this extra map or everything is because of how Hive is with combined input formats and Hive input format defaults and all of those kind of like crazy combinations. But at a high level, this handles pretty much incremental query, a snapshot query. It just filters the files. And then if you look at it, we'll call super, somewhere in here, we'll call super dot list status. And then, from there on, we just filtering files here. And this is how our implementation works for copy and write with both Spark, Presto, and also Hive or any engine. We don't try to control the record reader. This record reader is, for example, only for the bootstrap scenario, we have to really do anything. Otherwise, all we do is like just hand you the whatever Hive is. So any fixes to the Hive record reader, we pick it up automatically. Right. That's kind of like how this is done, and it is very different for the snapshot query. Which we call the Hudi Parquet real-time input format. And by the way, these are the input formats through which we register the table using Hive. So as you can imagine, the table has to be registered with these input formats so that we can do this filtering and give you transactional reads, right? Otherwise, there's no intelligence to interpret the Hudi timeline or the file groups. So what you will end up is like you will either get read all versions of Parquet files there, and then get duplicates or read incomplete in-flight files, and they may be partially written. So you can run into like a bunch of issues like that. So yeah, other than that, this one actually we override the record reader, where we use our own record reader here, and this is something that we are going to be investing a lot more on improving. So the design of Hudi, where we push the updates into the base file itself, the deltas, that kind of already gives us a lot of performance benefits compared to some models like Hive Asset, or where this like log the deltas and walk away. But still, I think we can still improve a bunch of these things in the merging. So we are working on some of that, including inlining the Parquet metadata there. But yeah, all of the merging code is here. Ultimately, this will call the log scanner that I showed before, right? And then the one other thing that was a little bit irrelevant, maybe irrelevant now, is this thing called Hudi path filter. We wrote a path filter, which is, I think this is being still used in Presto, no longer in Spark with 0.9. But it basically filters given paths and engines for, again, based on Hudi transactionally, what is the snapshot that you should read. The problem with this with Spark was, I think this was what the Spark folks recommended to me back then when I was writing it at Uber. But then over time, it is done very serially on the driver, which was not very performant for large tables. So we moved away from this to a more internal implementation for Spark. But this is still used in Presto. I think once we remove that, maybe we may can this file. But this does have some core functionality today. And moving on to how Spark is done, right? Any questions so far on the Hudi Hadoop MR? All right, cool. So Spark, everything lives in the Spark data source package now, which probably should be renamed differently. But it's a little bit confusing, this one. Most of this craziness is because of how kind of like Spark breaks between versions in, again, like some reckless ways. So what we have is Spark 2 and Spark 3. These modules are just like adapter layers where some APIs in Spark are different across these versions. We try to like write these adapters here for the different versions and keep them maintained. But most of the, if I recall correctly, this one is pulled in by Spark. This pulls in Spark client. This is the common code for like a lot of the Spark implementation, and you will find that this has like this. No, I think this is just mostly for some kind of packaging convenience. It just has the options and everything. That's all. This just anything that is common for Spark is what we have here. So coming back here, the hierarchy here is Hudi Spark ultimately pulls in everything. So we wanted to not break any, like people we're using Hudi Spark to write their programs, right? So to maintain backwards compatibility there, we did it this way, I think. So this has most of the code. And you can begin here, which is the point data for everything for reading and write. Whenever you're doing spark.read, like format Hudi, or spark.write.format Hudi, this is what gets invoked. And you will see that here there is distinctly, there is a method. This is still V1. We are again V2. So yeah, this is something maybe like worth understanding. See, this is the V1 API in Spark, and V2 is still experimental after 4 years for whatever reason. But the V1 API in Spark data source gives us a data frame and then lets us do whatever we want with it, right? Which means we are able to implement our nice write pipeline this way. However, this means that we are on V1 and V2, not on V2, right? So we've been like, a lot of our work around Spark integration has been trying to balance the features that we need in Hudi against the Spark V2 API. We do, for row writing, for example, we wrap the V2 API over V1, and to get like performance for writing, where we take the data frame and then we never convert it in anywhere and then directly send it into the storage as rows. So there's some like a lot of these other code that you will find here, which is all, I think it's called like Procreate. Yeah. Oh, this is all here. So this will be find a bunch of writer reader code here, which does some of these data sources. But by and large, this is the code, and this is where the Spark streaming sink is hooked up. So most of the writing entry point for Spark streaming is this, but most of the writing, I think you want, with the class that you want, is this guy. This is wrapping all of this upper level functionality. It's essentially wrapping a write client and doing everything. So when you're doing async compaction, triggering, or anything really, it's all, this big write method branches out. I think if anybody wants to like, help, I think refactoring this into more nicer pieces it is like a good good thing to take on. But it will essentially, operation wise, it'll switch into different kind of like things, and ultimately it calls if you look at it, it'll call the write client here. It'll say, write client do something. That's more or less what it does everywhere. So it's basically like a wrapper on top of the write client to do all your Spark reading. And all of the SQL stuff, actually, so we have SQL support now, right? So all of that is through this kind of like session extension, where we have our own parser for SQL, for have our own resolution rules and all of that. All of this sits in the, yeah, I mean, you may wonder why it's sitting in Apache Spark, and I think this is the way you, I think, can extend it. Unfortunately, Spark does not have good, publicly well documented sort of like internal APIs, right? You have to fish around Apache Spark code to really extend it. So yeah, this is all this code. All of this sits here. Like you can see that. If you want, for example, if you're looking at, hey, there's this create table command that is giving me an error, I want to understand. Then you go here within this command folder, and then you will see that, this is where the command is getting implemented. This is what is getting called. And once again, this will just wrap the right line. That's all. Just want to check if I covered, yeah, most of it. And then the grammar is in this file. And we are going to have to extend the grammar, I think, ourselves, because the way Spark works is, I think, even speaking competitively, like they introduce some keywords into Delta Lake first, and then Spark, like for example, the merge keyword wasn't even in Spark until Spark 3 was released, right? So which means we can't really do merge keyword when, let's say, Delta Lake has it, right? So there are these like kind of like gotchas around it. So we have our own grammar now, so we can actually add more and then be like, extend it the way we want to do it. So that's some background context into how this is all set up, and this all evolves pretty well. I think if you are looking for debugging list performance or things like that, that you can also look into this like Hudi file index implementation, which honestly is this is again implement some other internal thing in Spark. Sorry if whatever I'm saying sometimes feels like I'm like, kind of taking shots at Spark. It's not really that, but I mean, this is like in some internal API. It's not documented as a public API or anything. But yeah, this is how what you extend and live with and upgrade across different Spark versions to keep things running. And this is it's very, very tedious, to say the least, to get. And I really love for Spark to kind of like mature and have more better publicly supported APIs, but they make it extremely hard for anyone else to extend Spark this way. And this pretty much is the file index where we have written a Hudi specific one where it can, it's aware of file groups and it doesn't, for example, cache everything else, just the latest file group and all of that to give you like good list performance for Spark queries. Any questions here before I touch upon like the utilities?
Basic question, Vinoth, on the read part. So if I understand on a very high level, the indexes are used for writes, right? So for better read performance, do we have any mechanism of using index or anything? Like what are the different mechanisms to have better read performance in Hudi? So one is the file listing, which I understand, but yeah, apart from that, like Z ordering, I saw that RFC is already there, but any other options to make the reads faster?
Yeah, so at a very high level, it has to be either like, layout optimizations or like something like, which is what Z ordering is, right? And then indexing, correct? So we are working, so I can cover, if you can hold on to this question for a minute, then I can answer it while we discuss the future plans. I can show you what we are going to do. Here quickly, what I'll show is for example, for file indexing, we are set up to do like, predicate pruning, like meaning we can filter the files based on the expressions in your read. So the APIs are being set up. We are trying to do some work around like redoing some of these indexes using the metadata table infrastructure. Then I think we'll start exposing all of these indexes through queries as well. So that's the thing that we're trying to do.
Okay.
Yeah, I mean, okay. Any other questions before we go? All right, cool. Right. Yeah. So finally, like the thing that I think a lot of people have come to like a lot, which is the Delta Streamer, right? Which is the ingestion tool. This is actually to me is one of the honestly the really good things about open source is that you can actually like everybody contributes towards things that makes everybody else's life easier. Um, so here you go. So the Delta Streamer, there's a lot more here. I can actually generally talk through this. So this is the main class for the Delta Streamer tool. Most of the writing happens here, and you will see that there are services here within this Delta Sync service. There is like a this is where all of the writing really happens. We try to keep this code free from any source specific logic. And then what you have is a bunch of like, there are transformer packages, built-in transformers. There are all these different sources that we have now, it's actually pretty reasonably rich at this point. So a source, and then this is very sparse at the moment. So we're also trying to looking at making this a little bit more Spark Flink agnostic. So this may see some changes, but at the high level, all you have to write is, you're handed a checkpoint and some limit. You extract this much amount of data from this checkpoint and hand data back, and then Delta Streamer can do the rest, right? So we have sources. We have a bunch of row sources. You can write a SQL statement. You can extract data from S3, JDBC, Parquet, CSV, ORC, and JSON. We have probably for testing. Yeah, cool. Avro, Kafka is basically what a lot of people use. So there's a bunch of sources here to build out the lake. And this is also some place where even if you're not you don't love working on like the lower level transactions and all of this, if you can contribute a lot on these things, they'll be like help the community at large. Schema, I think we have the schema provider thing where it now has support for like a bunch of different ways for pulling schema for these external tables. Let's say you have JSON and then you want to enforce a schema, you can do that during ingest here, right? And then there's a bunch of things around checkpointing we can, for lack of time, I'll stop here, and then before they go spend the remaining kind of like 7 minutes on where we are going and important RFCs and what we're doing really around the project. But any questions before that? There's one question in my questions. Oh, no. Okay. Cool. All right. So this is roughly what is going on. I also will share this a little bit outside so that people have understanding about what's being done, right? So to answer your earlier question around indexing, so this is the root work that we just landed, which is the new synchronous metadata. So previously we wrote the table metadata and we just sync the file listings over, but file listings are small, right? But we want to add more heavier record level indexes and like more voluminous indexing, or even stats for that matter. If we want to really store stats for like a large tables with lots of columns or something, or you want to do streaming ingest where you're writing small files, then your metadata is going to like until we do some rethinking around this, the metadata is going to explode, right? So we've done that basic work here, and then we have actually PRs up now for record level index. This is being driven by Uber, where they're trying to replace their HBase index with this. And file listings has been already reworked and I think landed into master. I think this is what Shiva was asking, testing for. Range index is something where we have a PR around Z ordering and Hilbert curves, which is I think almost ready. It is going to go out in the next release. I just haven't found some time to like do a little bit more testing to land it. But we are also trying to move bloom filters out, ranges. So we are, and then there's another thing for bucket index. So there's a bunch of things here which are around indexing that are actually have either PR, more all, I think, except for maybe range index, bloom filter index, I think all of them have some PR up, right? So we're trying to put a lot of weight behind this cluster here, and then get this done. Once, so in this release, we may just expose it to the writer to just like stabilize things a little bit. And then once we, and parallelly, we'll be like, working on exposing this out to queries as well in point. So point 10, you may get most of these indexes, and point 11, we will start exposing even point lookups to these indexes, because we can then start doing more fancy things with joins, right? You can do UUID joins very easily. There's a whole world we can unlock once we get this. So we are laying all this foundation here. So that's where, test helping us like with development, contributing to the development and helping us test this even more. That'll be like awesome. And the other thing that is going on is we traditionally have supported schema on write, correct? Like we haven't, because I mean I worked at two very large companies where we did Avro schema on write, but so I like Uber and LinkedIn. So I think it can be done, but we do recognize that people want to do destructive, backwards incompatible renames or things like that. So there is actually work going on around that, driven by I think Huawei folks, with Robinhood as well. And yeah, that is going on. We are working on a bunch of like PRs are up for Parquet inlining, different merge optimization. So these are things that we largely want to get done. There is like a DynamoDB log service that is being added by AWS to make it easier to take logs across EMR clusters and things like that. And we are also doing a whole bunch of like foundational cleanup here, and some of them may introduce like new we may introduce like a new merge hook API to kind of like going forward replace the payloads, but we'll keep backwards compatibility for the payloads. But the idea is we want to like free ourselves from Avro and kind of like deal with the readers and writers in a more native way. So these are some of the things that we are currently working on. And the other thing is to also iron out some of the like the main pain points around this. As you know, like I don't know if you guys have had a chance to check out some of the stats, right? We get like ton of things for like like still a volunteer run kind of like project, right? And a lot of the PMC, yeah, we have to we're trying to track all these issues and at least get everyone to like a point where at least the broad set of issues is covered. So this is roughly the plan for point 10, and I'm going to like share this out in later today as well, and see what it's not just me, right? Like the rest of the community has to ratify and vote this, but this nonetheless represents what is going on right now. Moving beyond this, there is a whole bunch of like new work that we're doing, right? With the metadata table synchronous thing, we already have some sort of multi-table transactions here. We going to want our index functions where we want to like start treating these things more and more. Where create index you should be able to do on a table, and you should be able to do to the table while other writes are running. So how do you reconcile this? A whole bunch of things that we want to do for kind of like non-blocking index building, and so it's going to be like a bunch of different like work. There's already a PR around encryption. Masking is something that we probably want to write some transformers at the top to kind of like properly hash records, and these are very easy good contributions that people can make to the project. But other than that, we are writing a whole bunch of like sources and all of that to make the project. The metaserver and the caching are honestly what is like very much more closer to my my heart at least. And then we are trying to write native Presto Trino connectors in addition to the Hive things that we have. There is like advantages to this, but we also want to open up the connectors, separate connectors, in addition to the Hive. So Hudi is integrated into the Hive connector inside Presto, right? Which gives us a lot for free. For example, Facebook did this Raptor project where they do a bunch of metadata, block table, like data caching. All that comes for free if you use the Hive connector. But for some reasons, for schema evolution or something, maybe we need to write our own connectors. So yeah, these kind of things we are doing while we are also looking to row writing end to end, not just for bulk insert, for every other operation, and sort of like go from there. But this roughly paints like what's kind of coming. This is superimposed on top of what I already had in the previous slide. And yeah, there's some important RFCs here: the ZR curve, the record level index, the data skipping index, where I think we can potentially do a 10x better job than some of these other formats where the stats is stored in a more flat file. And hash index, I think I looked at it. It has some comments to be resolved. Kafka Connect, we want to have some at least immutable data with all the table services, at least immutable data with deletes and clustering. We want to support in the next release. And yeah, schema evolution, and you can see these labels. The big ones, I've been marking them as needle movers, if you will. Any large changes to code or any large re-implementations. So you can follow along on some of these things as well. Any thoughts, comments?
So thanks, Vinoth, for doing this. I think it was a good start for newbies like me to start looking more into more. Thanks for this.
All right, and yeah, I think we should do this at a also more regular cadence. We can at least do one per quarter, I think. That way, not one per year. That way, we can keep onboarding new people, or like once every 2 months or something like that. So again, thanks for doing this. I know like last time I initiated it, then I kind of like forgot that I didn't remember to do something. So thanks for getting me to actually do this actually.
Yeah.
Thank you.
Vinod, I have some general questions in general. Why these are the scenarios I observed while deploying some of tables using Hudi. Like in general, if we do any action on my table, we provide some configurations. So at the end, we are not sure like which are configurations are being used while the table is being inserted, or any place to view internally which configuration is used to do this operation. Is it logged anywhere?
So all the configs themselves are documented, but yeah, maybe I'm not probably fully understanding this. Maybe why don't we follow up on Slack or like the mailing list?
Yeah, sure. Yeah, that's all I have, I think.
Okay. Cool. Thanks everyone for taking the time.
Thanks a lot.
All right. Thanks, Joanne.
Thank
Bye-bye.
you.